We made a website to help people with finding related seminal papers when researching new technical subjects. The problem we're trying to solve here is that generally, when doing research, you have a single starting point, like an article. And from that article, you search for others related to it. However, starting from a single piece of information, it is hard to identify what else to read. For instance, looking at information theory, I would first go to Wikipedia page. Here, for the most part, I can familiarize myself with the basics. I was searching how to use information theory and where it has been used. So I found an article, a piece of information about semiotics. Here, I see there's different cited articles. Luckily, Wikipedia lists their cited articles in the end. So I looked in the citations and I find New Winfried's Semiotics of the Ideology article. I opened the abstract and read the intro, and I found some new things about semiotics. However, the paper was from 1981, and I was interested in where this has been used other than then. So I opened to see where the article was cited before, and I found an article about structural semiotics in marketing research by Laura Ruth Oswald. This just shows as to how complicated it can be to look for articles when doing research, especially since you have to read the abstract, you have to look at the intro, and then when you get to the citations, there's about 20 citations in each article, and it's hard to decide which out of these papers are related to the things you're researching. So, our solution was to create graphs of related papers to make it easier and visualize it for people to see what articles are related to the subject they're researching. Node.js was used with Scholarly for scraping the Google's API, which we use to see the relations and citation counts of the articles. The more the article is cited, the more relevant it was to us. Node.js was used with Electron to create a client app for a desktop on Linux and Windows. HTML, CSS, and JavaScript were used for front-end with GraphicWiz to visualize our website and give an experience for the user. The team consisted of me, Jovan, I did the front end, the CSS, HTML, as well as the API in case we decided to move from GitHub to a server-based hosting. Erica was making a database for keeping the information that was scraped from Google Scholar's API. And Edward did the overall backend, so scraping the Google API, creating of graphs, rendering the graphs, as well as a desktop app for the client.
For the project, we put everything in one GitHub repository. On GitHub, we have a wiki explaining some of the more confusing things users might want to know, like how to read the graphs, how the settings work, and a few solutions to common issues. GitHub also hosts the Windows, exe, and Linux DEP and RPM files that people can download to run the desktop app. Additionally, there's a zip file with a Chrome cookie getting extension. In the src folder on GitHub, there's a folder db with all the 90,000 JSON files, a folder Electron with the source code for the Electron app, and a folder Chrome cookie getting extension with source code for the Chrome extension. For a while, we were thinking of having a backend with a user database to serve data to the users, but we ultimately ended up going with having a set of about 2,000 pre-searched research fields, which totaled about 90,000 Google Scholar queries, stored as JSON within the GitHub repository, and served via the JS Deliver CDN. The web app version uses GitHub Pages, which dynamically makes calls to JS Deliver as needed in order to make the graph requested by the user. To traverse the graph of articles, we use some heuristics combining the number of times an article has been cited, how many clicks away the article would be from the original query, what year it was published, and a relevancy score that was increased if we encountered the article multiple times while traversing the graph. After the graph is sufficiently searched, a GraphViz script is generated that will make an SVG of the graph with color-coded nodes of hyperlinks to the article the node represents. In the event that the user makes a search on the web app that requires data we didn't pre-scrape, the user will be prompted to download the Electron app. With the Electron app, we no longer have to worry about cross-origin resource sharing restrictions and can scrape data from Google Scholar on the user's own machine. We considered having a server dedicated to doing scraping on the back end, thus making it so that users wouldn't have to download a desktop app, but that proved to be impractical given the rate-limiting restrictions Google Scholar enforces. Electron uses Chromium as a user interface, so we could reuse a lot of the code from the web version on the desktop version. It also made it easy enough for us to make cross-platform support for Windows and Linux. Fortunately, I don't have a Mac and didn't have time to look into what it would require to add Mac support as well. That's something we could potentially add in the future, though. Figuring out how we would get data from Google Scholar to the web app was one of the biggest hurdles we had to overcome. Google Scholar will only allow you to make about 40 requests in succession per IP address before it requires you to answer a CAPTCHA. Cross-origin resource sharing restrictions also meant that we can't have the client's browser scrape Google Scholar even if we wanted to. Our initial idea was to have a database connected to a backend scraping script that would scrape Google Scholar, and then via an API we could retrieve the data on the front end. This proved impractical, though, due to the rate limiting I just mentioned. We would only be able to scrape about 2 graphs a day, and that's just not sufficient. We also briefly considered having the database be filled with data scraped by the desktop app, which fixes the CAPTCHA problem, but opens the database up to vandalism or other malicious user actions. After some research and testing, I discovered that by answering CAPTCHAs and then giving the scraping app the request cookie, we could scrape about 500 requests per CAPTCHA answered, and a seemingly effectively infinite number of queries per day. This is much better than 50 queries per day, so we decided to go with a pre-filled static database, which ended up really just being a bunch of JSON files. Since we could only search a limited number of things to be stored statically, to determine what things would be best to search, I wrote a simple JavaScript snippet to turn all of the fields in the List of Academic Fields Wikipedia page into an array of strings. That gave me an array of just over 2,000 strings, each being a different field of research. I then put the data into the Electron app, along with a snippet of code that automatically sequentially searches each graph, saving all the results into a JSON file as it goes. For each search term, it made about 50 Google Scholar queries. Every roughly 500 Google Scholar queries, Google Scholar would demand another CAPTCHA to be solved. To do this, the Electron app prompts the user, and you need to go to Google Scholar, answer a CAPTCHA, and give the subsequent request cookie to the Electron app. I wrote a small Chrome extension to make this process a little bit easier, since I had to do it every minute or so for about 5 hours to scrape all the data. The Chrome extension adds a tab to the Chrome DevTools so that it's only one click to copy the Google Scholar request cookie, which can then be pasted into the Electron app, allowing for a few more graphs to be made. Once it was done, I ran a different piece of code, which took the JSON file of all the data and split it up into 90,000 small JSON files, one file for each Google Scholar query.
Development and deployment. Our code is open source. Here is the name of our GitHub repository name, Literature Review API. Below that are the links to our GitHub and Heroku web application repositories, respectively. This application was initially deployed on GitHub, but then that was changed to Heroku, but then changed back to GitHub. More on that later. Lessons learned. Overall, we definitely took away something new from this internship. From personal experience, I know I took away more than one new thing to learn from this internship. One thing we learned was that Electron makes cross-platform development relatively easy. That's handy to know, especially for a novice programmer like me who's just starting out, or for somebody who is in a time crunch, or simply running an agile sprint. The second thing we have learned was that GitHub can manage over 90,000 files, but it takes a while to upload them. Something to think about when, for example, I'm adding data to the database, or when someone is adding new code to the application. It might just take a while for the program to update itself, or something like that. And the third is we got more experience working on a cloud-based environment, which in this case was Heroku. And of course, last but not least, trial and error for writing and testing code, such as, is this program functional, or are there any errors that could be preventing this program to run? Further work. If time permitted, here are some more components we would have added to this application. The first is machine learning. It would be great to teach the application to, for example, sort the documents of data by their search terms upon recognition without even any prompting. And the second is that it would be great that because there's always so many changes in the academic world, because there's always new discoveries, that we could have the machine learn how to adjust to changes in trends and whatever data is being collected. And earlier I made a comment that when I said about how to sort the documents by their search terms, I will go into more detail with that later. And then the second is dynamic database. And okay, this is where the documents come in. I actually suggested that I was hoping that we could deploy a MongoDB database. MongoDB database is a NoSQL platform. And I thought a NoSQL platform would be the best way to address a dynamic database. Seeing that it can handle different varieties of sizes of documents of data, so to speak. In fact, at the time of this recording, I'm still working to make that happen. Earlier, we mentioned that we made the change from GitHub to Heroku, then back to GitHub. And that was because we had a static database, which leads me to the last point of this slide, which is learning more about how web scrapers work. One of the things we noticed was that there were certain scholarly articles, websites, search engines that had a very low rate limiter. So we had trouble where we would attempt to scrape a certain amount of data, but however, that amount was exceeding the threshold of how much data we can scrape from it, and we winded up being locked out of the system. So we are hoping to learn more about web scrapers, about how we can make our application more efficient, and work perhaps with those CAPTCHAs that were making that rate limiter so small. And hopefully we can get the application running more faster and get more data. Here's our contact information if you have any further questions. Thank you so much for taking the time to hear about our application. We hope that you enjoyed learning about our web application as much as we enjoyed